cloud native system. With that, over to you, Akhilesh.
Hi everyone. Yeah, good evening everyone. Thank you for being here. Myself, Akhilesh Bolam. I currently work as a software engineer at Amazon, building large-scale cloud native systems with a focus on real-time synchronization systems. Today's talk is sync or sync because in distributed systems, data synchronization isn't just a feature. If you don't get it right, your system eventually syncs. So in this talk, I'll try to focus on some of the practical lessons with respect to real-time synchronization systems, like what tends to work, what tends to break, and some of the mechanisms that we can look into that make these systems resilient. So why does this talk really matter? Real-time systems, they are usually not judged under stress conditions. They are not judged under healthy conditions. They are usually judged under stress conditions like network outages, dependency slowdowns, or peak traffic events. But as far as end user is considered, they try to expect different features like the data has to be fresh, or it has to be correct all the time, and there shouldn't be any duplication as such. And the UI has to transition from one page to another very smoothly. They also look for offline safety so that whenever they become online, the data has to sync right. In reality, distributed systems, like, they tend to introduce lots of delay, duplication, and disorder. So with that being in mind, you have to build your systems in a very resilient manner. That way, you don't end up with a lot of outages. So because of that gap, like, resilience cannot be something we add later as a patch, but it has to be built into the system from day one. So whoever is working on this, like, they have to think this from day one. So with that context, let's look into what we'll go today. So we'll mainly go into some of the mental models that are required for building such systems. We'll look into some of the baseline and production architectures, some of the failure modes with some real postmortems, and some case studies and examples, and a final playbook that everyone can take away from this talk. So before we go into architectures and failures, let's try to understand how widespread this problem is. You can find real-time synchronization everywhere, in messaging apps or e-readers, where you try to read a book and try to annotate or highlight something, and you expect the data to be present across all of your devices. You'll find in live dashboards and monitoring systems, and it's also widespread in financial systems where you have to deal with lots of critical data altogether. So to address this problem, let's start with a simple mental model. So this mental model contains three concepts, mainly state, events, and deltas. State is nothing but it tells you what's the current snapshot of data in your system, and events tells you like what really happened, and deltas tells you what's the difference between one state to another state. So getting this mental model right is very important, but many of the real-time systems, like, they get this wrong, and they try to mix up these ideas and try to interchange them. So like, if you treat events like states, you end up overriding the data, and if you treat states like events, you can replay incorrect history. And if you ignore deltas altogether, then you try to waste lots of network bandwidth and increase latency. So coming to the baseline sync architecture, it's quite simple. There's a client that's trying to send requests to backend API, like an API gateway, and it does publish the data to some of the messaging queues. And there's a worker sitting around trying to consume the data from these queues. So while the architecture is very simple and easy to understand, and it works reasonably well at small scale, but this design hides several assumptions. It assumes retries will fix failures. It assumes queues will observe traffic spikes, It also assumes that eventual consistency means eventually correct. So with these assumptions in place, they might work for small systems, but they tend to break down as the scale increases. So in production grade systems, you know, right, like it's a huge scale and we tend to get lots of traffic. Now let's look at how production grade sync architecture looks like. Overall, it follows the same baseline architecture, but with some additional safeguards embedded into this. So instead of a simple queue, we use a durable event stream that gives us persistence, ordering, and replay capabilities. And coming to the consumer groups, they are organized into multiple groups, so multiple workers can process in parallel. And writing to the databases are one version or condition, so that stale updates cannot go into a system. And results are cached for fast reads, and failures are isolated using delta queues. And importantly, every stage becomes observable where we measure lag, throughput, error rate. So production systems, like, they don't replace the baseline architecture as is. They keep the same behavior and shape, but internally they try to harden the system with these safeguards so that it allows the system to tolerate all these inconsistencies like delay, duplication, and disorders. So at the heart of the most production grade synchronizations is the event-driven PubSub backbone. This system supports lots of features. Mainly, it supports loose coupling, where producers simply publish and there are consumers independently listening to them. So this decoupling allows each side to scale independently. The system also supports durability. For whatever reason, if consumer crashes, it can restart and resume from where it left off. And because events can be replayed, we can recover from bugs and backfill new consumers easily. And it also does support fanning out to multiple consumers, so that you can notify different processes that you can find in the system, like analytics team or notifications team or any other synchronization processes. While this PubSub system is a powerful building block, it does not really give us the data correctness. It all depends on the guarantees we choose. So let's look at some of the guarantees that PubSub systems try to give. These are mainly three: at most once guarantee, at least once guarantee, exactly once. In the at most once guarantee, it guarantees fast delivery with low latency and high throughput, but it's possible that messages can be lost. So it's mostly used for non-critical telemetry systems like metrics collection or log aggregation. And coming to the at least once, it provides more guarantee and more high reliability, but it's possible that duplicates can be possible, and you require your applications to be handling these duplicates. And there's another third one, which is the exactly once. It's one of the strongest guarantee, but it requires extensive coordination and high cost. So you'll find this guarantee to be used in critical systems like financial transactions. Coming to the production rule, most enterprises, like, they try to default to at least once delivery combined with idempotent processing. Now let's try to look at some of the failure modes, starting with retry, storm cascade. In one of the real incidents that we have observed, it all began with a downstream latency spike. Like the P95 latency jumped from around 200 milliseconds to 9 seconds. Because of that slowdown, multiple clients timed out and triggered retries. Those retries quickly multiplied the traffic about 8 times. Very quickly, corresponding queues started backing up. Within a few minutes, the backlog exploded to millions of messages. At the same time, database connection pooling became fully saturated, and multiple dependent services began to experience failures. So this kind of created a feedback loop. Like, slowdowns caused retries, retries caused more load caused more slowdowns. Like, we had an entire outage that lasted about 18 minutes. So if you closely observe, the system was not overwhelmed by real user traffic, but it's overwhelmed by its own retry traffic. So in conclusion, like retry storms are essentially self-inflicted outages. So what did the system really do wrong? Like where did it go wrong? It wasn't using exponential backups whenever clients are retrying the request. There was no jitter as such, and there was no cap on the number of retries that were happening, and there's no circuit breaker pattern in the system due to which unhealthy dependencies were continuously hammered instead of being isolated. And there are some handlers that are found to be non-idempotent. So what really changed or what really fixed the problem? The system started to incorporate exponential backoff and jitter. Retry budgets were considered, and there were maximum attempts enforced globally. Some circuit breaker patterns were enforced so that the system can fail fast on unhealthy dependencies. And there are other things like bounded queues, idempotent keys, and some of the observability that's incorporated into the system. So coming to the second failure mode, thank you. Yeah, I'll quickly go. So there are other failure modes that's possible, like unboarded queues. Queues are often used to observe spikes, but queues don't remove overload. The backlog tries to grow very fastly, so you have to address this. There are some methods to address this, like you can configure the queue to be bounded, and you can apply some techniques like back pressure, auto scaling, and you can prioritize critical data over non-critical data. And the third failure mode is the consistency conflicts. There are different types of strategies to address this, like last write wins, or version updates, which can handle stale updates not going into your system, or operational transform or CRDTs, which are really useful in collaborative apps like Google Docs. There are different adaptive sync strategies that are very useful. On a high level, I'll go through a simple case study. As you all know, people across the globe, they use large-scale e-reader platforms to read ebooks, and they try to expect their highlights or notes to be available across devices. But users started reporting lots of issues like missing highlights, last read position frequently inconsistent, full sync transfers. They made heavy readers very slow, and reconnect storms caused latency spikes. So what was the original design? There was no prioritization around critical data like last read positions, and someone was trying to do full sync rather than delta syncs. So what really changed? The system started to use delta sync protocol, where clients fetch only the change that was required since the last successful sync. Critical data like last read was downloaded first, and other data like other highlights or notes are downloaded in the background. And there were other techniques like idempotency and reconciliation engine that were implemented to handle out of order events. Overall, like these are the different metrics that matter the most when you build a real-time synchronization system. From user perspective, we have to track end-to-end latency and data freshness, and from system perspective, we have to track retry rates, consumer queue lags, throttle rates, and out of order rate. So this is a simple battle tested sync playbook which tells you what to do and what not to do. So everyone can try to follow this playbook when building real-time synchronization systems. Yeah, that's it.
Awesome.
Thank you.
We'll take one quick question. Anybody have one quick question? If not, please find Akhilesh after the talks. Thank you.
Thank you.
Akhilesh. With that, we welcome our second time speaker, Pragya. She's speaking at this meetup second time. Very fortunate to have her.